So let's just get started. So on Monday, we just learned that uh, gradient can help us to get the tangent plane. So if you want to get the tangent plane, when you are giving the service, the function, then the first thing for you is just get its gradient first. So the gradient vector, you can just regard gradient vector as the normal vector for the tangent plane，就是那 gradient vector 实际上就是一个切平面的法向量，你其实就是可以这样想哦。Then I also told you that actually there are two forms. The first form is maybe the service will just be given as f of s y z is equal to c. Then the second form is just like this one, z is equal to f of s y. Actually, they are almost the same. The only difference is in such a form, maybe it just look like blah 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 x plus blah 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 y, and blah 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 z is equal to c. But for this one, it is just explicitly represented as z is equal to f of s y. But no matter this one or this one, almost the same. You can just follow this idea to get the gradient vector. Then the gradient vector is the normal vector for the tangent plane. Okay. Then we also learn another thing for the application of the gradient vector. This is we just use the gradient vector to get the rational derivative. Then we can just estimate the change in some specific direction. So just like this one. So if you just cannot understand the concept, you can just consider to just review the concept you learned for single variable, just like this one. You can see the change in f can be calculated by the derivative at some certain point times a small change in x. So similarly, for this one, if you want to know the change in f, I mean the function, then you can just calculate the rational derivative first and times a very small change in this direction, so that you can get the you can just estimate a change in some specific direction. Then I also show you an example like this one. So today I will teach you about the linearization. Linearization of a function f of s1 with two variables at s0, y0. So before I just formally introduce the linearization for a two variable function, I just like to spend some time to review the concept in single variable. So for in single variable, this is for single variable. Normally we will have y is equal to f of s. Then I also will focus on some specific point. If this is y is equal to f of s, then if we just focus on a, then we can just get its function value is f of a, right? So when we talk about the linearization for the single variable function, we are talking about the tangent line here. This straight line, this is a straight line, is the linearization for y is equal to f of s at s is equal to a. So we need to assume f of s is differentiable at s is equal to a. So that means we can calculate f prime a because it's differentiable at s is equal to a. So f prime a means the slope for this straight line. So we just define L of x is equal to f prime a times s minus a plus f of a. Then we will say this is a linearization for y is equal to f of s when x is equal to a. So as I told you, different a will produce different linearization, right? So for example, if a is here, a prime, its corresponding linearization will be this one, right? So at the same time, we also learn about how to apply linearization to approximately calculate something, right? So this is the purpose for linearization. So if we just encounter a function which is a two-variable function, that means z is equal to f of sy. The linearization for a two-variable function that will be L of xy. See, there are two variables. Is equal to f of s0 y0 plus f partial x of s0 y0 times s minus s0. Then plus partial f partial y s0 y0 times y minus y0. So this is the linearization for a function which contains two variables at s0 y0. So you can just also can understand that if we just type y, you just ignore y, then ignore y, you can see they are the same. If you just reduce two variables to single variable, it will be the same. Okay, this is one point. And the second point, actually, if you just want to visualize it, it will be just like that. If y is equal to f of sy, z is equal to f of sy. So when I give you z is equal to f of sy, then you can construct its surface, right? So the surface will be like this one. So I just want you to have some comparison between this one and this one. This one and this one. So when we just fix S0, Y0, for example, S0, Y0 is here, that is just equivalent to A. Okay? Its rho, S0, Y0 in the plane is equivalent to A in the x-axis. Okay? So, and the surface here, actually they are same as this rho. Okay, so right now, what is the linearization for a two-variable function? This time, the linearization for two-variable is the tangent plane pathing s0 y0 then f of s0 y0. So tangent plane is equivalent to the tangent line. So you can see the rho here are corresponding to each other, right? For the function itself, z is equal to f of sy, it will be a surface. But for single variable, I give you y is equal to f, it will be the curve, right? I ask you to focus on some specific points. For single variable, we may focus on a, so that we have a corresponding function value that is f of a. So similarly, for two variable functions, we focus on s0, y0. So its corresponding pi is f of s0, y0. So that means this point will be represented as s0, y0, then f of s0, y0. So its corresponding tangent plane will be a plane, right? Compared to single variable, it will be a tangent line. So we can say actually the tangent plane. This plane is L of sy is equal to f of s0, y0 plus partial f partial y, partial f partial x, f of sy, s0 y0, s minus s0 plus partial f partial y, s0 y0 times y minus y0. Okay, so just remember there is a actually the rows are almost the same. So I will give you an example that the example is just like this. Find a linearization of f of sy is equal to s squared minus xy plus at 3, 2. Okay, based on this, we need to focus on partial f partial x at this point, right? So we need to calculate partial f partial x. That will be 2x minus y when sy is equal to 3, 2. So the answer is 4. So we will calculate f partial y at 3, 2. Then that will be negative x plus y at 3, 2. So the value is negative 1. Right? So right now we already the first partial derivative for partial f partial x. And we also have the second one. Then we just put them together. That L of sy is equal to f of 3, 2 plus partial f partial x 3, 2 s minus 3 plus partial f partial y 3, 2 y minus 2. So finally, through some calculation, the answer is this one. So this is a linearization. So I'm not sure if you also think about it. On Monday we just learned how to, when I give you f of sy is equal to blah blah blah, blah 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 y at some certain point s0 y0. Can you just get its tangent plane? Actually, the tangent plane is just this linearization. So I also can show you by using what we learned on Monday. Okay, so did you think about that? On Monday, or maybe we just make it smaller so I can have a full. You can see the full picture for this one. So this is S, this is Y, this is Z. So this is, I assume this is f of sy is equal to Z is equal to s squared minus sy plus 1/2 y squared plus 3. So at this point, this is 3 2, right? This is 3 2. Focus on this one. So we can have the corresponding point here. That will be 3 2. Then you can just use 3 2 to get its height. That will be 3 square minus 3 times 2 plus 1/2 2 square plus 3. So that will be 9 minus 6 plus 2 plus 3. Right? So it will be 8, right? It will be 8. So that means A will be here. Right? 3 2. When I use this as the input for this function, then I can get its height is 8. So the point will be 3, 2, 8. Right? So on Monday, we just learned that the gradient vector for this point will be the gradient vector. So I can change the form as s squared plus sy plus 1/2 y squared minus z plus 3 as 0, right? So I can change it as this one, so that I can define s squared. I can define f of xyz is equal to s squared plus minus sy plus 1/2 y squared minus z is equal to -3, or plus 3 is equal to 0. Both are fine. You can just move plus 3 to right hand side, become -3, or you still keep 3 at the right hand side, and its return value should be 0. Okay, so once we get a function, so that we can start to calculate gradient vector, right? So the gradient vector will be partial f partial x partial y partial f partial y partial f partial z at 3 2 8, right? So we can get that will be 2x minus y, then negative x plus y, then -1 at 3 2 8, right? So the result is 4, -1, then -1. So remember, in such a solution, we just get the gradient vector first, right? Then we just try to get its tangent plane. The tangent plane here is this one, right? Did you still remember? How can we just control the tangent plane? For any point xyz here, we can make a vector. Then this vector must orthogonal to this gradient vector. So we can try to get that. So the xyz is an endpoint minus the start point 3, 2, 8, inner product, the gradient vector 4, negative 1, then negative 1 should be 0, right? Should be 0 because they are mass orthogonal for each other, right? Then after that, we can just do some calculation on this, so we can get 4 times s minus 3 times negative 1 times y minus 2 times minus 1 times z minus 8 should be 0. Then we can continue to calculate. It will be like this, so that you can see it can be 4x minus y, then negative 2, negative z is then negative 2 is equal to 0. So did you notice that you can see here this tangent plane, by following the rule we learned on Monday, we can calculate its tangent plane is this one, right? So did you notice this one is same as this tangent plane is same as this one. If you regard L of xy as z, right? Z is equal to 4x minus y minus 2. So if you just move the z, negative z to the right hand side, it will be z is equal to 4x minus y minus 2 as well. 哦，所以大家有没有注意到，事实上linear来讲在做什么事情？实际上就是做切平面。所以如果大家把刚刚这件linear来选当做我现在好像定义一样，可是大家仔细去观察，它事实上在做什么事情？不妨想想礼拜一教大家什么。如果刚刚我给你一个曲面是长这个样子的时候，这个一点你可以利用 gradient vector 去算出它的 normal vector， 对不对？就是切平面的法向量。上次有跟大家讲过，我给你一个法向量，再给你一个通过的点，我就可以唯一决定那个平面，那个就是我们的切平面。所以这个我这样在导这个过程当中是帮大家礼拜一的观念再复习一次。当我给你一个点经过3、2、8，在这个曲面的基础之下，我要算出它的切平面呢，基本上我就是在做什么呢？就是先把它的 gradient vector 先算出来，好，所以这个 gradient vector 是4、-1、-1，黄色的这个。那我怎么去建构这切平面呢？我教大家一个技巧，任何上面在这个切平面上的点叫 SYG， 这个点到这个通过的点之间可以建构一个向量，不管它这个 SYG 在哪里，只要它是在这个平面上面的点，它拉一个向量出来呢，这个向量呢应该要跟它的法向量做垂直正交。那我们知道两个向量如果要正交的话，是它的内积要为0。所以经过这个内积算，算出来，哎，这个切平面叫做 4x 减 y 减 e 减2。那大家对应一下刚刚学到的 linearization， 我们定义的 linearization 是 L(f(x)y) 等于这个算出来是这个。你有发现，其实他们两个一模一样，所以这也就是更加说明了，在一维就是单变数函数的时候，我们在算所谓的 linearization 的时候，事实上是在算它的一个切在某一点上面的切线。但是如果把它 extend 到二维的函数的时候，它是在算它的切平面。所以相对于切 linearization 在单变数的时候，它事实上是在算这个切线的方程式 对于两个变数的函数的时候，它相当于在这个曲面上面，在这一点上面做出来的一个切平面。哦，所以当然用这样对等去想的时候，你心里面要记的东西就少很多了。如果当时你忘了把这观念衍生过去，你就知道它两个都是在做切的动作，只是一个在切曲线，一个是在切，一个是在切的直线上，一个是在切的平面上，这样。好，这是 linearization。那当初 linearization 还记不记得单变数的时候，我们的 linearization 是要做什么？去概算，如果这个点在这附近的值，我可以用这个切线来计算。所以大家应该也可以衍生这个想法，是按linearization在对于两个变数的是要做什么？其实也是一样，我可不可以在这附近做一些微小的变化的时候，我可以不要带到原来的曲面上去算，而直接带到切平面，因为在这附近，你们发现这附近 A 的前后一点点的地方，其实你把它带进去原来的曲线所得到的值，跟你把它带到切线上面的值会差不多，会有小小的误差。同样这也是，但你离太远的时候，还记不记得我在当变数讲linearization的时候，如果离太远的时候，这个linearization的效果就不好，因为这个差距就太大，这个 gap 这 error 就太大了。但是只要在 A 的一点点的变化，一点点的地方，其实你可以用这个来估算。所以接下去我们就要讲怎么样用这个来估算变化啊。那这个我们就导到下一个我们要讲的观念。Okay, so the next concept I want to introduce to you is the total differential of f of sy. So if we move from s0, y0 to a point s0, y0 plus dx plus dy. So did you remember when we talk about d blah blah blah, d blah 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 differential? That means in this direction, the change is very small. The change is very small. So dx s plus dx, that means 1 point. D is just around s0. So similarly for two variables, dx for x direction, dy is for y direction. Very small change in s direction and also in y direction, which the resulting change df can be defined as partial x partial f partial x s0 y0 times dx plus partial f partial y f s0 y0 times dy. So this is a small change in sy with dx dy that will cause a small change in f. Maybe not small change, but the corresponding change can be defined as like this one. So I believe you also still remember that for single variable function. For single variable function. So when we define one function y is equal to f of s, then we also focus on s is equal to a, its slope is f prime a, right? Then if we have a small change in x direction, df can be defined as f prime a times dx. The corresponding the, the, the resulting change is defined as f prime a times dx. So you can just simply move dx back to the left hand side. You can go back to get df over dx is equal to f prime a, right? So we also explained this idea to you before, because you can see if we just focus on a, we can add prime a here, we can get a slope. If you want to know the change, the small change from a to a plus dx, here, if a to small change to like a plus dx, so the corresponding change this is df, can be regarded as slope times dx, and you can get dx. So we just apply the idea to the two variable function. You can see if we just hide y, you know y part, it will just go back to the single variable function case, right? Okay. So I just give you an example. So please just make a comparison between single variable and two variable function. Okay. So I just give you an example. The example, maybe I can show you the example in the still the same page. For example, if there is a can, this is a can, right? Then we know if we want to calculate a can, the volume V should be defined as pi r square h, right? Pi is a constant, r is the radius for the base, and h is the height, right? If we want to calculate the volume. So right now, this is a typical example. But now, for example, if the original, maybe let me just draw another one. If the original base is 3, this is 3, and its original height is 12. Then we want to make a small change in its radius and its height. So if we just slightly increase its base, we just increase it by 0.08. So that means its base r is from 3 to change to 3 plus 0.08. It's not so, it's a little ugly, right? Because the number is very small. So the radius becomes 3.80, 0.8, okay? And its height, we just lower its height. Lower its height from 12 to, this is a new can. We just reduce it to -3, -0.3. So the high, original high is 12, but the high will be from high 0.3. Okay, so the high is from 12 to 12 minus 0.3. So of course, you can just calculate the change by, this is a new can. This is a new one, right? This is the old one. So of course, you can just use pi r 1.7 square times, no. You can use 3.08 square times 11.7, right? This is the new V. This is the V for new, right? But for old one, it will be pi r squared times 12. This is for old one, right? So if you want to calculate the distance, the difference, you can easily to get from V new minus VO. This is a very traditional way to know the difference between the new can and the old can. You can just simply use this one to calculate, right? But right now, if you know how to apply the differential, we have another solution. Another solution is approximated result. The absolute change can also be in the volume of the can. Is almost calculated as dV. dV means the change from the new one to the old one. Okay? We can use it as V partial R of R0 X0 times dr plus partial V partial H R0 H0 dH. So the original R0 H0 is 312, but right now we just change to R0 plus dr, H0 plus dH. That means 3 plus 0.08, 12 minus 0.3. So you can see this very small change in R, then there is a small change in H, right? So based on this, you know that we can almost estimate as 2 pi R0 H0 dr plus pi R0 square dH. Then we can just put, this is R0. I can point out that this is R0. this is dr, this is s0, this is dh. Okay, so you can just apply these numbers to here, then you can get the approximated change is 9.161 cm cubed. So here, v partial r, based on, why can we just get this one? This is easy, right? Because why can we just get this one? Because since v is equal to pi r square h, so we can regard v as a rh function, right? So when we calculate vr, means partial v partial r, so that will be 2 pi r h. Partial v partial h is equal to partial v partial h, so it will be pi r square. Okay, so we can just use that for here. Then we can use here from here. Okay, so that means you can see originally we need to calculate this for new. This is for old. Then try to get its difference. But right now we have another solution. We can use the total differential. We call it total differential. This is the total differential to calculate its approximated change. Then the result is the next one. Okay, so this is about this section. 11, 12. Okay, let's just take 5 minutes break. Okay, 5分钟休息一下哈。Print values and settle points. This session we will talk about extreme values and settle points. So I believe you can just understand what extreme value is, right? Because when we just learn differentiation, we already know. I mean, for single variable function, we already know we can use the first order derivative and the second order derivative to calculate the extreme value, right? So it's no doubt that you can understand what extreme value is. But in single variable, we will not, in a single variable function, we will not have settle point. Only for two variable function we can have settle point. So in this session, we will discuss these two terms. So let me just introduce what is the local maxima. What is local minimum? So if f of AB is a local maxima value for f of x1, if f of AB larger than or equal to f of x1 for all domain points s1 in an open disk, centered at AB. So actually, the concept is quite similar for single variable function. The whole idea is just like this one. Or maybe I just write down two extreme values definition first, then I can draw a picture for you. If A prime, B prime, another point is less than or equal to f of sy for all domain point sy in an open disk centered at A prime, B prime, then we will say this is a minima. Sorry, this is a this is a maybe I just made some mistake. Okay, here if we say f of A prime, B prime is a local minima value of f of sy. So let me just remove this pinpoint. If okay. So if f of AB is a local minima, we need to satisfy this requirement. If f of A prime, B prime, A prime, B prime, this is A prime, just provide the minimum value for f of sy if f of A prime, B prime less than or equal to f of sy for all domain point sy in an open disk. In an open disk, it should be in an open disk. So I can draw the picture for your reference that z is y. So this is the local maxima. This may be the local minima. The surface is just like this open disk, and for the other part, they may do like this one. And for this case, for example, if this is a local maxima point, this is a local minima point. If you can find in some certain, so for example, if this is AB, and this point is A prime, B prime. So if you can find an open disk containing AB, then you just map all points in this disk. So we can just map it here. Okay, then you can see all points. If you just map any point in this open disk, then we just map to this function value. You can see f of AB is larger than or equal to f of sy. So similarly, if you want to get a point provides minimum value, so using A prime, B prime as a center, then we just you can always find a disk, then map to the surface. You can find here the function value here is f of A prime, B prime. This is F, A, B. Then you can see maximum value is always larger than its neighbor or equal to its neighbor. But for the minimum value, this point is always lower than its neighbor or equal to its neighbor. So this is the local maxima and local minima. Okay, so this is a very simple example. Then I'd like to show you another special point. Oh, as for the settle point, later I will show you. Then in this case, we also need to define the extreme, the critical point. So if f of xy has a local maximum or local minimum value at an interior point AB and partial f partial x partial f partial y exists, then we must have f partial x at AB this AB is equal to 0, and at the same time f partial y at AB is also be 0. So did you remember compared to single variable? We also know this before, right? For single variable, y is equal to f of x. So at that time, did you still remember there are some possible points we can find? Oh, maybe the shape. I need to slightly adjust, something like that, right? This is A, this is B. So we say if we can find some interior point, like this point or this point, if we can get maximum value, right? You can see for the green point, they are interior point, right? They are not endpoint, they are interior point within A and B, right? So if they just located in the interior as an interior point, you can see it's for this C or this C, we always can f prime C is equal to 0. I mean for the interior point. At that time, we also know that endpoint may possibly provide local maxima or local minima. But for interior point, if they provide maximum value or minimum value, local maximum value, local minimum value, we always can have its first derivative is equal to 0. Horizontal line, right? Only horizontal line we can going up and going down, or going down and going up, right? It is differentiable. So you just apply the similar concept to two variable functions. If two variable functions for some interior points A and B, A, B, and partial f, partial x exist, that means differentiable. For single variable, it should be differentiable. For two variable, we just need to assume, we just need to have f partial x, partial y exists. Then we can conclude that its first partial f partial x at this point and partial f partial y at this point must be zero. Must be zero. So that based on this idea, we can also define the so-called critical point. Did you still remember critical point? Critical point means the point is very important. They have some spatial characteristic. So what is a critical point? We just define it as an interior point of the domain of f of sy, where both partial f partial x is equal to 0 and the partial f partial y is equal to 0, or where one or both of partial f partial y partial f partial x do not exist. Then such a point, we call it is a critical point of f of x. So similar for single variable, I believe you also still remember that for the critical point for single variable, we also know that in such a case that maybe in this case or in this case, this point f prime a is equal to 0, or in this case f prime a doesn't exist, because this is the slope is positive infinity or negative. But for this case, it's a horizontal. So at that time, we also define this is the critical point for single variable, right? But right now, we need to define what is the critical point in a two-variable function. So we just define it like that. If the point is the interior in the domain, then either both of them partial f partial x or partial f partial y, both of them are 0, or one of both does not exist. That means maybe the partial f partial x will have a positive or negative infinity value. Then we will call this is a critical point. So I always show the case in single variable function for your reference here. You can just have some kind of comparison in between. For single variable, it's just like this. So you can just intuitively accept the concept for two variable function. This is also for single variable, and then you can just try to image in two variable function what will it look like. Okay, then I will define saddle point. As I said, saddle point only happen in two variable function. In single variable we will not have. So what is the saddle point? So the saddle point is defined as below, that a differentiable function f of sy has a saddle point at a critical point So that means center point must be a critical point, AB. If, okay, the condition is just like that. If every open disk center at AB at this point, then there are several xy points where f of xy is larger than f of AB. And at the same time, and, okay, if every open disk also centered so maybe I already defined that. So there are some sy where f of sy is larger than f of ab, and there are also some sy where f of sy is less than f of ab. Then in this case, a b f of ab, this is the space point on z is equal to f of sy, is called a saddle point. Of f. So I can draw the saddle point for your reference. So if this is s, y, and z, right? So the so-called surface is just like this one. You can just image that this is the surface. So you can see this is the surface, okay? Okay, this is surface. So in this direction, you can see if AB is a saddle point, this is AB, right? And this point is AB, then f of AB. Then this is the surface. This surface is a little bit changed. In this direction, you can see, some point just larger than f of A. Some points just larger than f of AB. So we can just use this as we just make a disk. This is the open disk. You can see part of name when we just map the point to the surface. You can see part of name for f of AB, for f of sy, here for f of sy, they are larger than AB. So we can see for this direction, you can see they are larger than f of AB. But for this direction, you can see they are this point, the neighbor point is less than. So you can see every open disk, part of them can map to some point, but f of AB is the largest one. But part of them in this direction, you can see f of AB is is the minimal one. Then we will say this is the zero point. 这个马恩点只有在两个变数函数才会有的，在单变数不会有的。哦，它的定义是这样的，就是大家想一想马鞍嘛，马鞍大家应该知道嘛，就是它会有一个方向看起来它是最大的，有个方向看起来它是最小的，这在单变数不会有的，对不对？像这个我画，不好意思啊，这个很难画到让你们很满意，但是你就想象这个曲面呢，当我给你 z 等于 f 的时候，就是白色的这一块，就是白色这一块，但是它的曲面有点奇怪，这边呢凹下去，从这个角度看它是凹下去的，可是从这个角度来看它的是，它是凸起来，所以马鞍点的定义是什么呢？就是如果这 AB 点是所谓的马鞍点的话，它所呈现出来的这个点 AB 逗点 f of AB 呢，它是既不极大又既不极小。怎么说呢？它如果它以它为中心，任一个 disk 的范围里面呢，把它带到这函数来，你会发现，从这个也许画的不是很好不过没关系，我约略可以画线，你大家也可以感受出来，就是如果黄色的是走的是这些点，你看它对上的是这些，对不对？这个角度呢，如果你从这个角度来看，经过 AB 这个角度来看，它对出来的点都是比 FAB 呢还来得高，所以从这个角度来看，从某个角度来看，它变成最小的。好，但是如果另外一个角度，橘色的随便说可能是这个，对不对？它对上来的时候是对到这边来。从橘色角度来看，你沿这条路线走，它也是经过 AB， 但是它投射出来的曲线上面的点，曲面上面的点呢，它变成又是区域的最大。所以你会发现这个点很特殊，它从某个角度看，任何 open disk 任何你只要以它为中心，画一个 open disk， 永远会有人比它高，但永远会有人比它低。那这个点你就称之为是马鞍点，单变数不会嘛，对不对？因为只有在多变数的时候，因为两个变数的时候，它才会有四面八方的考量，在单变数它只有一个走向而已。Okay, so then we also have a theorem to support us to calculate the extreme value. We call it second derivative test for local extreme values. If f of s1 and its first and second partial derivative are continuous through a disk centered at AB. So that means if in AB we have its first and second, okay? First and second partial derivatives. So first is this one, right? Second is include these four ones, right? Did you remember first partial derivatives? We just differentiate f one time with respect to x or respect to y. So that will be partial f, partial x, partial f, partial y. But at the same time, for his second partial derivative, What is the second partial derivative? Partial f, partial x, partial x, partial f, partial y, partial y. And you also have partial f, partial x, and then partial y, or partial f, partial y, and then partial x. 4 possibilities. And for these 4 second partial derivatives need to be continuous through some disk at AB. And then the important thing is if partial f, partial x of AB is equal to 0 and partial f, partial y at AB is also 0, then 4 possibilities. The first case is f has a local maxima at this AB if partial f, partial x less than 0 and partial f, partial x times partial f, partial y minus f, partial x, partial y squared larger than 0. So remember 2 conditions, this one and also this one. Or the secondary condition is if f has a local minima at AB, if partial f, partial x larger than 0 and partial f, partial x, partial f, partial y minus partial f, partial x, partial y squared larger than 0. So please just notice that here and here, this is for maxima, this is for minima. So this condition is the same for both. But the difference is this one. Did you still remember when we just calculate the second derivative for single variable function? We just talked about its concavity, right? 它的开口，在单变数的时候有没有？我们二次微分是在考虑那个点的开口朝上或朝下，对不对？所以我请大家这样记了哈，这个后面这个就都一样，等一下我们可以用一个判别式来记这件事情。所以这个很好记，为什么？你看这也是双二次微分，只是它是二次的偏微分，它小于0，开口朝下，极大值；大于0，开口朝上，极小值。那后面这个是大家共同要遵守的条件，那就没办法说了。但是很好记，你先判断它是不是这个。如果是这个是成立的话，只要判断它的二阶导数的 partial x。那你会问到，那为什么不是 partial y？ 其实是一样的，其实会是一样的。partial y 的大会是同时大于0或同时小于0。The third condition is f of s has a saddle point at AB if this discriminant. Later on I will show what is the discriminant is less than 0. Then that will be a certain point. Then inconclusive. That means I cannot determine if this discriminant is equal to 0. So you can notice that this discriminant is very important. So we also have a notation for this one. You can use this discriminant. 行列是判别式哈。用这个来记啊。它的计算法则就是这个乘以这个，减掉这个乘以这个，这是减，这是加。这个方向 f， 它需要 f， 它需要 x， 它需要 x 乘以它需要 f， 它需要 y， 它需要 y， 这个减去什么？这两个相似就是二次方，出一个加一个减。那这个判别式就很重要哈，这个判别式决定了。所以通常做法是这样：当我给你一个 z 等于 f(y) 的函数这曲线的方程式的时候呢，你呢第一件曲面的方程式呢，你第一件事情就是先算这个判别式。判断方式是这个判别式先看它有没有小于，如果小于0 ，OK， 满足第三个这个点呢，就会是一个马鞍点。好，如果是大于0的话，你再进一阶再去分。如果两个是大于0，就是这两个。那看它的 f 的对 x 的二阶导数呢，偏导数呢，看它是大于还是小于。小于0，开口朝下，极大值；大于0，开口朝上，极小值。那万一这个判别式呢是等于0，那就没办法决定，我们就没办法决定，可能用其他方法，去做运算So before we go to the end, I'd like to give you an example so that you can just have some impression about how to use the discriminant and how to use the rule to distinguish if we can have a extreme value at some point. So in this case, f is defined as this one, right? S times y minus x squared minus y squared minus 2x minus 2y plus 4. So we can check f of sy is defined at all s and y. So that means there is no boundary. All sy prime, all sy in the sy prime, right, is the domain part. Then we can continue to calculate we try to define its critical point. So to find the critical point, we can find where to find the point, to find AB, where partial f partial x is equal to 0, partial f partial y is equal to 0. Okay, so we are trying to find some points. Maybe here. We are trying to find some points at AB where is partial f partial x is equal to 0, and also partial f partial y is equal to 0. So we are trying to find some candidate point. So based on this, partial f partial s is equal to y minus 2x minus 2 is equal to 0. Partial f partial y, I think this is not a complicated calculation, so I believe that is easy for you. So you can calculate partial f partial x like this one, partial f partial y like this one. So if it can be 0 and also it can be 0, then only s is equal to y is equal to -2, so that we can conclude -2 may, remember may, that means I still cannot conclude if at -2 negative can have an extreme value, but right now it's a candidate point, right? May have an extreme value of f of y. So this is the first stage. Then we continue to test this point. We continue to test. So we can calculate partial f, partial x, partial x. It will be, we continue to differentiate, it will be -2, right? Partial f, partial y, it will be -2, no matter what point, right? When you differentiate, it will -2. This is -2. Then when you use these two ones to calculate -2 is -2. Then use -2 as an input for this is also -2. And we also have partial f, partial y. Partial, then we differentiate this. Then we can get this is partial. Then we just differentiate it with respect y again, so that we can get this is 1, right? Because we can get this one, that continue to differentiate it with respect to 1. So we can get only this coefficient will be that. Then for the rest part it will be 0. So we can get partial f, partial x, partial y, -2 is 1. So with these factors, we can continue to get this discriminant is equal to -2 times -2 minus 1 squared. So the answer is 3. So you can notice that this discriminant value is 3, positive. So did you remember when we encounter the discriminant is positive, it will belongs to either case 1 or case 2, right? The discriminant here is 3, so positive, so it will be this case or this case. Then we need to continue to determine, to know f, partial x, partial x. So we can see plus partial f, partial x, -2 is also is equal to -2, less than 0. So we can conclude f of sy will have a local maximum value for the value is 8. Okay, so no worry, I just give you a simple example. Next week we can continue to focus on similar problem like this. And we also can use the discriminator and the rulers to check if there is any extreme value there. Okay. So let's just call it a day here. 好，那我们就上到这。